I'm going to go through some of the theory. If you guys want to move ahead to something, we can. But I think it's cool to think about what we're dealing with in our pocket here, and actually what we're dealing with in our cell phones and so much other devices out there in electromagnetic waves. Right? We know what mechanical waves require a medium in order to transport their energy from a location to another. So a block of wood or water, what have you, sound waves that will transfer through a medium. Electromagnetic waves is a wave that is capable of transmitting its energy through a vacuum. So you don't need a medium for it to go through. So we can transmit through space where there's no medium required. They're produced by vibration of charged particles. This is what's happening in your transmitter. If you look at things that we deal with every day, it's a really wide spectrum of radio waves up into infrared, microwaves, ultraviolet, soft X-rays, gamma rays. Actually, right here, the rays that we actually see with our eyes. So now our eyes are the antennas, and we're picking up the color waves. Right? It's kind of weird to think about that, but those are electromagnetic waves that we're picking up and viewing with our eyes. Where we usually live with wireless microphones is in that UHF range, the VHF range down here. STL band is satellite telemetry band that a lot of broadcasters use. You have to have a license to operate in that range. We're actually developing some wireless mics in this range because that's about almost 20 megahertz worth of space that we can utilize in the UHF range. And then, of course, our eyes, our antennas, our eyes are the antennas for the visible spectrum. So think about all those wavelengths that are flying through us right now. So actually a lot of them you can't see. When we think about a wave, a transmitted wave, a carrier frequency, this is the medium that we need to modulate this signal with audio information, right? So first we have to have that carrier frequency. When we think about a carrier frequency, we think about the wavelength of it. How big of a wavelength is it? How much power do I need to push it? Very important. So as a manufacturer, we think about different spectrums and what we would have to do in that transmitter. When you look at a wavelength, we always say 550 megahertz. We say kilohertz a lot, all these different numbers. What does that mean? Well, 1 hertz is 1 cycle per second. 1 megahertz is 1 million cycles per second. So if that means 500 megahertz is 500 million cycles per second. So that transmitter is creating a wavelength 500 million cycles per second in that little AA battery transmitter. I think that's incredible it's able to do that with the technology that we have now. It's actually old technology, been doing it for a long time. But I think it's really cool when you think about how many cycles per second we're actually transmitting. So that means 500 megahertz, the higher the frequency. So 500 megahertz, if I jump up to 700 megahertz, the smaller the wavelength, right? If I go to a lower frequency, 500, 400, down to VHF, then the longer the wavelength, okay? Do we care about that wavelength and how long and how short it is? How come?
Propagation.
Wave propagation, right. When we think about manufacturing a wireless system, we love being in UHF range because it has the best all-around wave propagation for transmitting a wireless microphone. This is why the telecommunication companies want to use this spectrum, because it takes less power to transmit a lower frequency than it does a high frequency. So if you take a 500 megahertz range transmitter and you got a 10 milliwatt power, and you take a 600 megahertz range transmitter and it's got 10 milliwatts of power, if all things equal, you will get further range and distance with the 500 megahertz than you will with the 600 megahertz. VHF, right, down in the 173, 216 megahertz will go even further, a lot further, if it was still also at 10 milliwatt. Now, I say that because sometimes you are running something in 500 and you're running something in 590 megahertz. If you need really long range, use the lower frequency to even get that extra 10 or 20 feet of distance. That can make all the difference in the world if you're looking for that range, if you're doing a long shot. A lot of guys will do this with the ref mic for an NFL, right? They know the ref's going to be all over the place, so we're going to give him the lower frequency, in the higher power transmitter that I have. So a lot of times I'll use our 250 milliwatt transmitter at a low frequency. Now he's going to be all over the place, and he'll have coverage across the whole stadium. And then wave propagation specifically, the longer the wavelength, the easier it can bend around objects and not be easily reflected and blocked. That's why we don't usually like to go up to the 2.4, the 1.9, 5 gigahertz and higher, because it's a much shorter wavelength and can be easily blocked. And because it's a shorter wavelength, there's more reflections within a room, creating more multipath. So the higher frequencies, smaller wavelength can be more easily blocked and needs more power to push it as opposed to the lower frequencies. There's a mathematical equation that shows you if everything was created equal and you didn't have anything in front of it, you weren't trying to go over any hills or anything, you would follow that mathematical equation and get an idea of how far you can go with a specific amount of power. When you look at our frequency finder, which we're updating now with FCC, we show a power of the transmitter. You put in your zip code, and then it shows you all the local transmitters and how close they are to your location. And it tells you it's 100 kilowatts, and then there's a reading of how strong that signal is at your location, and it's using that calculation based on a clear transmission path. Then you got to look at building attenuation and things of that sort, or hills and things of that nature. You guys are going to learn about waves like you never. I think it's cool, but you know, I work for Sennheiser. So this is us now looking at, it's actually a time lapse of the wave, right? It transmits, the wave is going through space and time. Here's a long wavelength, low frequency, and then we move up to a higher frequency, more wavelengths, shorter wavelength as well. Right? That's what it looks like when we look on a spectrum analysis of it. Typically, when we look at, like when we just look at the DTV channels, we were looking sort of straight on at the frequency. We're just looking at gain of the transmitter. So here is a transmitted frequency, a carrier frequency, unmodulated, and that's what it looks like. Let me bring it up on the spectrum analyzer. So we're just looking at the power of this transmitter. It's going into this antenna, and it's going into the receiver here. What we're seeing is, if you're wondering about this noise here, I'm overloading my spectrum analyzer a little bit, so I'm getting a little bit of noise in the transition as it comes into the receiver. Now, but what does that look like in a spectrogram? So here we are looking straight at it, and here's our transmission strength, and here's a spectrogram showing it over time. So I can actually change the wavelength of it, the power of it, and see how it transmits over time, this 470 megahertz. Here's the noise floor. There's some little frequencies popping up down here. That makes sense? So you can see it in time and distance, and then you can see it just as a power fluctuation. You can see these popping up around here, which is the probably the public safety stuff happening down here. I'm just detuning the antenna to bring the RF down a little bit. Thank you. So just a quick diagram to show that I was talking about in relationship to frequency. If everything was created equal, you go the furthest distance with the lower frequency. That's why a lot of anybody doing shortwave and the really low band stuff here? Anybody do that? Those guys can transmit, really far on very low output power across the U.S. at a very low frequency, and it just bends around the terrain and hits from Maine to California. So just some frequency ranges. We know we're now, I have to change that. It's now 608 megahertz. We're still looking at VHF. There are some manufacturers that are going back down the VHF now. I think it's a valuable place to be. Does anybody have some old VHF equipment? Works great, right?
Pretty damn good at it.
Yeah, yeah, and you get really good range with it because it's a lower frequency. I say save that VHF stuff and hold on to it. It could be a lifesaver if you get interference in the UHF. 902 to 928, this is a unlicensed range. You'll see a lot of garage door openers. We make some wireless headphones in this range. It's not a bad range to be. It's decent wave propagation, not much bandwidth down there, up there, but not too bad. And this is the STL band I was telling you about, 941 to 960. I think that's another valuable spectrum that we can use. It'll probably be open for a while. I know a lot of broadcasters use it. Some rental companies are using it. So I've seen rental companies use it. If you do use it, since you're not a broadcaster and it's a licensed spectrum, you can still get a license for it. No, not a license, but a temporary license. If you write the FCC, there's an application. You can say, you know what? I own these, and I'm going to have it on the show for these 2 months. This is the transmission power. This is the area I'm covering. I'm doing it as a test. The FCC will say, okay. How much? 50 milliwatts a device? I don't care. Go ahead, do it. And it's a very small charge to do it. So I've done it as well. I know Soundtronics does it out in LA.
You can't get a Part 74 license.
No, you can't, but you can do a temporary license, and usually it's an experimental license.
Mm-hmm.
We were doing silent discos for a long time. Everybody go to a Sennheiser silent disco? And I was operating in this range. Well, in this range, you can only transmit at about 2 milliwatts, but we built a transmitter that was doing 100 milliwatts, and I would put on a powered antenna and just blast the area. It's really illegal. And we did the silent opera in LA years ago. In fact, me and Rod worked on that.
Okay.
And I couldn't take the chance, to do that for, that's gonna be months and months and months. So we did a temporary experimental license saying, we got this device, this is the range, this is the area down at the railroad station we're gonna do it at. And they said, okay, it's okay, go ahead and do it. So that is valuable resource there and something that you guys can do on a temporary basis. This spectrum is what we're seriously looking at in other manufacturers, the 1.4 to 1.5 gigahertz range. It's now used or shared with flight training, but it's something that we're looking at to utilize with some new devices. They're still working out with FCC if that's going to be okay, and how they can still keep the flight training protected from interference. But that seems like a good propagation and a pretty wide range of 100 megahertz that we can utilize. So that may be something we use in the future. 1.9 megahertz we're using now, 2.4 we're using now. There's latency in some of these. You got to be careful of that. DECT can be pretty high latency, up to 19 milliseconds, depending on the device. But I've seen a lot of broadcasters use them for the E&G gear for just short range, a couple of channels, and covering news events and so forth. Be careful of the Wi-Fi. More and more 2.4 and 5 gig. It's unbelievable what we've seen in theaters and so forth. I think I was working at the Harry Potter show in New York, and they had 32 access points in the theater. It's not counting stuff that was coming in from outside. And we were trying to set up we make a mobile connect device, which is a Wi-Fi device. We finally integrated it into their system because there was no way. Then you get into the higher range. It's okay for short range application. In this room, a couple antennas, you're not looking for a really far range. I think the way we look at things now, there's not that silver bullet anymore of that this wireless will work for everything. It's really going to be application based as to whether I need the range, how many channels do I need, what's the best application for that range. I'm seeing a lot with the broadcast sports productions now, where they've spread their frequencies out all over the map now, utilizing every bit of spectrum depending on the application. If they don't need great range, they go up to the higher range. How many intercoms now are up in the higher range, right? That changed considerably. Actually, it was good because it opened up in-ears and UHF down below.
Well, now you go to all the stages here and all the timber board operators
are using
lights.
Oh, right? Yeah, so that's the you got to keep up with it, right? Because you don't know what's going to come out next that's going to be utilized in that range also, especially when it's unlicensed up in the higher gigahertz range. Yep. All right, we talked about the bands of frequencies. We know it's 6 megahertz. You go past this. This is just showing the old analog channel when we talked about putting a couple of frequencies between the picture carrier and the sound carrier, which you can't do anymore. This LA. This is LA's public safety. And that was not hard. That was not hard to get. It was consistently bang, bang, bang. Unbelievable. This was on top of a building in LA when we were doing one of those silent productions. But you can see how sharp these and how strong these signals were. So you really had like right around in here to work with, and that was about it. So next year, Sennheiser's going to start selling Sennheiser cable. Hardwired mics, they're coming back, guys. No, that's not true. Okay. I think we know we need a device that transmits a signal, electromagnetic waves, and then a receiver that brings it right back. And of course, really most important stuff is antenna, right? If you don't have a good antenna or good antenna placement, that can be the death of any good system out there. Such an important part of what we do is that antenna part. I've seen a lot of installs where people kind of scrimp on the antenna side of things, right? I'm sure you guys have worked on jobs or like, and then we're gonna have to put antenna. No, I can't. I don't have any money for really good antenna infrastructure. So when we think about modulation now, you saw the carrier frequency. So now we got to modulate that carrier frequency. So we generate the pure carrier, modulation of that carrier with information to be transmitted. Any reliable, detectable change in that carrier characteristic could carry this information, this audio information. And then the detection of the receiver strips that information off of the carrier frequency. But I want to show you what that looks like. If you look at what we're allowed to do, FCC regulates that we can only do 200 kilohertz deviation. So we got that carrier frequency. We can only deviate that signal up to 200 kilohertz, right? Or 100 kilohertz on each side of the carrier frequency, no more than that. So we have to have the best sound quality with that 200 kilohertz that we can do. So let's take a look at what that looks like. So you can see as I talk into it, right? You get the deviation of the signal. Eventually, it is limited, so it can't go over the 200 kilohertz of deviation. This is called a wide band or wide deviation for a carrier frequency, right? Unlike what would have a narrow band transmission as opposed to a wireless microphone or a stereo transmission for in-ear monitor. Walkie-talkies, right? Really narrow deviation. We don't need a lot of audio quality because you're just talking, instructions and so forth. So yes, walkie-talkies are generally very narrow band. Also intercoms, right? Intercoms are very narrow band typically because you just need nice communication. You're not going to broadcast with it. But with wireless mics and also in-ear monitors, we need to use as much of that 200 kilohertz as we can. And the more that we can saturate that signal, the lower the noise floor of the audio signal, and the better the quality and frequency response you're going to get on the deviation of that carrier frequency. What are these two little things here? 1, 2, check. 1, 1, 1.
I was going to say, those are your harmonics as far as.
Right? No, you would think it would be.
I mean, I see one's a little bit further out as far as that goes.
It is our pilot tone. Yeah. Pilot tone is a 32 kilohertz tone that we send to the receiver. Sort of a key. The receiver is looking for these little pilot tones on each side of the carrier frequency to say, hey, I'm your transmitter, so open up, squelch, and receive me, and everything will be okay. It's a safeguard so that when you do turn your transmitter off, and there's a frequency that's right on that carrier frequency, the receiver will not automatically open up, squelch, and say, oh, it must be the signal I want, and it outputs it to your audio output. So it's just another safeguard. I can actually turn it off. There. I can turn it off actually, so that now if I turn off this transmitter and if the receiver did see another signal that was strong enough, it would output out of the receiver and maybe give you a big loud noise coming out of it. So just a little safeguard that you have for it. So the way that we can change these characters of the frequency is through amplitude, phase, or frequency. What I just showed you was FM or frequency modulation, right? What's the other modulation is amplitude or AM, like sorry, AM radio, right? The problem with AM radio or amplitude modulation is when that signal comes down, all the audio quality is built in the strength of the signal. Think about your AM radio and your radio. Who listens to still the AM radio? I do too, right? Your AM radio, you go into a tunnel, as soon as that signal comes down, you start to hear the noise, right? Shh, comes in. Because all that amplitude comes down towards the noise floor, and all the noise comes back into the signal. With FM, regardless how strong that signal is, you're still going to hear quality audio. So you take that same tunnel with your FM, your frequency modulation, even though that audio, the gain of your transmitter comes down, you will still get a strong quality from the FM signal as opposed to the AM signal. So when FM was introduced, that was huge for wireless microphones and FM radio and so forth. The quality went way up regardless of how close you were to the signal. So if you're picking up the radio and you're 50 miles away from the station or 10 miles from the station, you got the same quality as opposed to AM, where that noise floor would come down, or the signal would come down into the noise floor, and you would hear noise coming in. So this is what we deal with now is frequency, also another way of you can call a phase of modulating that carrier frequency as opposed to amplitude. And this just shows you the difference in the modulation. With amplitude modulation, you're modulating the signal as a strong signal and modulating it down to a weak signal, back and forth, back and forth. With FM, we're expanding and subtracting that frequency range above and below the carrier frequency.